Thank you so much for having me. It's really amazing to be here. It's amazing that I can come virtually. And yeah, I'm sorry that I can't be there in person. It sounds like it's an absolutely amazing conference, but I just can't get on planes anymore personally. Like I don't fault you guys at all, but I just I was on a plane in 2012. I was still part of LIGO at that time, and I was going to a collaboration meeting in Europe, actually. And as soon as they shut the door on the plane, I was thinking about my little kids. And like you said, I was getting very worried about climate change at that point. So I'm like, I just don't want to do this anymore. Anyway, I feel a little bit like an imposter in your conference too, because I'm not a super SciPy evangelist. I am I feel like I'm just sort of a normal user, and I'll tell you some of the things I use it for. And I'm extremely grateful that it's there. A lot of things that would take me months or even maybe years to develop myself, and that would be full of bugs and would take a lot of testing, and wouldn't feel confident about it. They're just right there in a package, and I can just call a couple of lines of code and it works great. And I know there's a huge user base. I know it's been tested and I know that it works. And that is, sometimes I think we in science take that for granted, and it's just such a valuable thing. And the other thing I want to point out too is that climate science is such a huge field. Earth science is such a huge field that any one of us in the field has these tiny little snapshots in terms of our research, and we don't always see the big picture. We don't know what kinds of software other people are using, et cetera. So anyway, without further ado, part of why I feel like I'm a little bit of an imposter, I think on April 6th, I did this climate civil disobedience action because, again, I'm starting to feel really desperate about inaction from world leaders, right? Earth scientists have sounded the alarm. We've done the science. We've made it really clear that we have to end the fossil fuel industry quickly, and world leaders aren't doing this. And so I don't, sometimes just writing papers and doing the science doesn't feel like it's enough at this point. So a lot of us scientists are starting to do more, and more than just march too. So I guess I will just jump into this talk. I'm not sure why. Okay, that's a weird. So three kind of parts to this talk. So the first part of this talk, I was thinking about just my own time as a programmer, my own kind of development, which started a long time ago in 1999. I actually started a few years earlier than that with a course called CS50 at Harvard when I was an undergrad. By the way, I should say that I'm speaking on my own behalf in this talk too. That's what I was thinking when I was showing that slide with civil disobedience. But anyway, this weird old book was actually my main entryway into programming. So I was teaching high school physics at the time in Massachusetts, shortly after graduating from college. And the tech boom was going on. The internet boom was going on. Everyone was rushing to start internet startups and whatnot. And I knew I was going to have to move to Manhattan in a few months and leave that teaching job because my wife was starting starting a master's at Columbia. So I'm like, what can I do? So I took this book, and I think I did take about 21 days to go through it. And I just really enjoyed the exercises in it and learning sort of object-oriented programming in Java. And I'm like, this is really fun. And I could see doing this as a career. So I went to New York and actually had my wife's mom, for some reason, had my one suit, like my one cheap suit, in her closet. So I had her mail it to New York and put it on. And I actually got the newspapers in those days. They had classified ads. And I went to a couple of interviews, and I got this job at this little boutique Java shop that was doing trading platforms on Wall Street, actually. And so I started getting into concurrent programming, multi-threaded stuff. I was using these technologies called Swift, which was in the news a few months ago, TIBCO, doing back-end stuff with SQL, not worrying too much about how kind of highly available and, important and, potentially catastrophic the failures of my software might be if I got it wrong. It was, I was just young and having fun programming basically in New York. After a couple of years at that first company, I started feeling like I didn't want to just help rich people get richer, basically. So on Wall Street. So I'm like, I want to go back to physics. I want to go back into science. I applied actually to grad school at Columbia, and I didn't get in. And I got a new job. This was after, so I'm not doing a great job telling my story, but 9/11 happened while I was at that first job. So much is coming back now. There was our company was attending a conference, sent a couple of people to a conference at a restaurant called Windows on the World on top of one of the World Trade Center buildings, the northern one. And I actually asked my boss if I could go to that. And I'm glad that he said, no, you don't have any reason. I was just curious to see what it was like and wanted to go up to that restaurant. And two key people from our little company were killed on 9/11 that day. And one of them was our key salesperson. And then after that too, there was a massive downturn in the market. It got a lot less fun. Being in New York got kind of weird. Being in the tech field got a little bit weird. About half of my company got laid off, and people were kind of demoralized after that. So I decided to get a different job. It was still on Wall Street. And one of the interesting things about it was it was one of the best bosses I've ever had. And he wanted me to explore aspect-oriented programming. And I'm not even sure if that's still a thing anymore, but I was doing it in Java, and it was really kind of cool. But that only went on for a year, because then I did get into graduate school at Columbia. And so then I was in the field of MATLAB and Mathematica doing physics problem sets. And then I decided to start working for LIGO. And that was my PhD thesis, was a search for gravitational waves from these highly magnetic neutron stars called magnetars. And I was still working primarily in MATLAB actually at that time. And I just want to say a little bit about this photograph because it's just so beautiful to me. So I remember this is the Hanford detector in Richland, Washington, sort of in the deserts of eastern Washington. This is a mountain called Rattlesnake Mountain. I remember the first time I drove up to the LIGO sign here out on the street there, and just this feeling of gratitude, I guess, of being part of creating knowledge, creating human knowledge, and understanding the cosmos. It took me a long time to come sort of back into science, basically. And I used to rollerblade along these 4-kilometer long arms here of the detector to go out and do work on the optics out there. And because there's these little nice smooth tracks alongside them. One time I hiked up to the top of Rattlesnake Mountain, even though it was I don't think I was supposed to do that. But what an amazing time. But yes, I got too worried about climate change. And I just couldn't focus on astrophysics anymore. I got a job at Caltech as a postdoc. I found I was spending more and more of my time reading climate papers. Eventually I just decided to switch into earth science. So I got a new job, another postdoc up the road at JPL. And then this was kind of my programming world. All right. So instead of books, I was getting my information from Stack Overflow. I think that's still my main source of kind of if I need to figure something out in Python, that's where I usually go. A lot of SciPy. And then every now and then I have to do something in IDL or Fortran or R. So actually, I usually for R, I'm calling someone else's code from Python. Okay, and so now I want to switch into kind of giving you a brief overview of 5 of my current projects and just a little bit about the kind of my experience with SciPy in those projects. All right, so the first one is kind of really data science-y project called Spatial Statistical Data Fusion. And so in earth science, especially what I do at JPL, involves remote sensing satellite data. So it's kind of messy because you have satellites orbiting the Earth. A lot of the satellites I use orbit in sun synchronous orbits so that they kind of stay, if you imagine their ring going around the planet, it's always facing the sun in the same way as the Earth orbits underneath it. So it means it's always passing overhead at approximately the same time, local time at every location on the planet as the planet's rotating. And you get these swaths. So here you can see for this particular instrument, this is near surface air temperature, 2 meter air temperature retrieved from hyperspectral infrared data. And you can see the 2 swaths there. That's one satellite overpass. And that's another satellite overpass there. That's actually the earlier one. And you have this missing data in between. You probably had a cloudy area over there. That's another satellite overpass. And this is a different instrument on the same day. And it just happens to, it's at a slightly higher orbit, and it's a different retrieval. It's a different way of getting the near surface air temperature out of that infrared spectral data. And so it's got different cover, different footprints. And we did, I basically used the spatial statistical data fusion algorithm that my collaborator, Hai Nguyen, had developed as part of his PhD thesis. He had written in MATLAB. I ported it to Python, and it was super easy. So I did unit testing. I think I used PyTest, and that was super nice because I would have some like dummy inputs into the MATLAB code and see what the MATLAB code spits out. And then I would just write a unit test and make sure that the same input into my Python code, that same module had exactly this, or within tolerance, had the same output as the Python. So that allowed me to port it in like about a day, or 2 days maybe. And I had to use these kind of new linear algebra packages that I hadn't used before. And everything was there that I needed in Python that he'd used in MATLAB, because it was some pretty gnarly linear algebra. And then I also started using Xarray for the first time in this project. And it sounds like a little thing to be able to read in NetCDF or other formats, but I mostly work in NetCDF with a one-liner in Xarray, and then to be able to write new files in one line. But it was kind of life-changing to move from reading in each variable separately and having to debug issues with offsets and scale factors and whatnot. So I would say probably Xarray is my all-time favorite Python package now. But I know a lot of you are thinking, oh man, he's missing out on some great stuff. And I'm sure that's true, which is part of why I want to leave a few minutes for discussion at the end of this if I can. All right, so that's that project. And we're applying this to other variables too from remote sensing. So it's a pretty general use thing, and I think it's a pretty cool, little way to do actual data fusion, which is going to become increasingly important as there's more sort of satellites up there, and scientists want to extract, all the information from multiple satellites, right? And it's extremely hard to do without some kind of fusion methodology like this. And we also do bias correction first using in situ land data, which is extremely sparse. So we end up with a bias corrected lower variance product with greatly improved uncertainty estimates too, which in my opinion is really, really important. One of the surprises coming from astrophysics was that earth science at that time sort of was played pretty fast and loose with uncertainty quantification, which was a surprise coming from Astro. Okay, so next project, trends in severe convective environments. So this is a supercell. When I started Earth Science in 2012, I was started in cloud physics. I was looking at low marine clouds over the eastern ocean basins, which reflect sunlight. And so this, I've since moved a little bit into kind of ecological forecasting and ecosystem work. So this is a bit of a vestige from atmospheric science, and it's interesting to me because it's one of the sort of last open questions. I mean, there's a lot of open questions, but it's a kind of an open question of great interest to me, which is how are these convective environments potentially changing due to global heating, and how could that? We need to understand how they are changing in order to understand how they will change in the future. So I've been kind of part of the AIRS science team. So AIRS is the atmospheric infrared sounder, and I've been part of that team for quite a while at JPL. It launched in 2012, so it's one of our kind of oldest satellite records of atmospheric water vapor and atmospheric temperature. So that's why it's a sounder. It's basically taking these profiles from space and looking at the different layers of the atmosphere and getting the temperature and moisture all the way up from the ground to the top of the atmosphere. And the fact that we have that data record from 2002, this is a 20-year data record, makes it extremely valuable for climate work, because it's very, very hard to get a kind of a good read on a lot of atmospheric climate trends with just say like 10 years, right? But because it's very noisy, there's a lot of interannual variability and multi-year variability. So to have a 20-year record is extremely valuable. And it's very valuable for looking at the thermodynamic environment of severe convection. The problem is, remember, it's doing that sun synchronous orbit. So we only have two snapshots within the diurnal cycle. When it's ascending, we get 1:30 p.m., close to the sort of the maximum of the diurnal cycle. And then when it's descending, we get 1:30 a.m. on the other side. But severe convection, things like tornado, hailstorms in this sort of tornado alley region, tend to happen a bit later. They tend to happen about 3 to 4 hours after that 1:30 p.m. overpass. So there's this temporal gap. So to bridge that gap, what a kind of method we developed was to use wind meteorological data to move around air parcels at every layer in the atmosphere, so that we could kind of reconstruct the atmosphere, say in like half an hour snapshots going like 6 hours into the future after that 1:30 p.m. overpass, and then reconstruct those thermodynamic profiles from which we could do things like calculate convective available potential energy, convective inhibition, and other indices to understand that convective environment. Now, why is this important to do with satellite data? Why can't you just use like weather balloons? The problem with in situ data is you get a very accurate view of the thermodynamics at that one tiny point. But you'd need, even to understand one supercell, you need several of those weather balloons all around the supercell. And it's very, very hard to get into position. You'd basically be sending tornado chasers out. It'd be extremely expensive, and you'd still only understand that one supercell, and you'd be missing a huge amount. So that's why it's important to try to kind of data mine the record from the AIRS instrument on the Aqua satellite. So some of the meteorological functionality to calculate those indices come from a package called SharpEye, which has made this project so much easier to do again. We also, and this, I wanted to point this out too, that when an atmospheric scientist or when another Earth scientist like has a very particular thing that they've solved. For example, David Romps solved the exact expression for calculating the lifting condensation level. They are more likely to publicly release that code in Python than I would say any other language by far. So he had this nice little script to calculate this, which he made publicly available, and we just used that and folded it right into the project. So it's not actually a package, but it's still, that kind of thing is still super useful too. And we got a ROSES grant like a year ago. So it's we started maybe half a year ago the project, and we're going to apply this methodology to the entire errors record, so that once we have that data record, we can start looking at how the severe convection has been changing over the last 20 years. Okay, next project. This one's brand new. I started it last year, and just with some kind of small internal pilot funding within JPL. And so this one's trying to use machine learning to understand and predict on fairly short timescales, so basically a week to a month, wildfires. So I think you all know, if you've, especially if you live in the West, but if you've been paying attention at all, it's the last few years have been absolutely devastating in terms of wildfires in the Western US as it gets hotter and drier due to burning fossil fuels. To me, this is one of the more terrifying impacts of global heating. In 2020, I lived through a crazy heat wave at my home here in Altadena, where it got up to around 115 degrees Fahrenheit. And I remember walking in the neighborhood and it felt like an oven. And I walked under this tree a couple houses down, and there was a dead bird on the ground. So the birds was overwhelming them. This extreme heat wave started a fire a couple miles away from my house called the Bobcat Fire, which burned through the San Gabriels, just out of control, almost burned down Mount Wilson Observatory, which is where Edwin Hubble discovered the expanding universe through galactic redshifts, right? So I remember watching the cameras that they had up there and watching the fires kind of coming up the mountainside. But anyway, hotter and drier conditions increased fuel load. So a lot of the trees have been succumbing to drought. A couple of years ago, my family and I hiked the like 90% of the John Muir Trail up in the Sierra Nevada. And it looked pretty healthy to just the untrained eye at that time. Last summer, we went back, and we went back earlier than we ever had, basically for the very early summer, I think in early June. And the change was devastating to me. There were so many dead trees, lodgepole pines. That second time, we were passing Pacific Crest Trail through hikers. I think most of them were seeing it for the first time and didn't really maybe realize something was amiss, but it just broke my heart to see the trees that had succumbed from that drought. Anyway, so our small team has created a machine learning model that can take in these features. I started this project kind of trying to replicate another model that was working on monthly timescales, looking at soil moisture and monthly average vapor pressure deficit. So vapor pressure deficit is a measure of kind of how dry and hot the air is around a leaf and how much it basically wants to suck the water out of the leaf. Like how much is that moisture feeling the need to leave the leaf and go into the air. So the hotter it is, the drier it is, the higher the vapor pressure deficit is. And so that's a good fire indicator. We were using a monthly average down version of VPD. And I felt like I wanted to try using a daily data instead, because of my experience in 2020, basically, I just felt like when you have these massive heat waves, it seems like they tend to set off wildfires too in quick succession. And so I wanted to test that hypothesis with this data. And so we actually used the near surface air temperature and the vapor pressure deficit from the Data Fusion project, which was cool, along with these soil moisture product from GRACE, which is uses gravity, changes in the gravitational field that it's sensing, these two satellites going around the Earth, to infer changes in hydrology on the planet. Like it's our main way of understanding, for example, how the major ice sheets in Greenland and Antarctica are changing. So yeah, here's a graph. It might be a little hard for you to see, just showing the change in the number of large fires from 1992 to 2018. So here's 2018, just have a lot more fires there. And so yeah, for this project, obviously we're using sklearn. Again, it looks like Random Forest is one of our best tools for this project, and it's just, again, such a boon that we can use this with confidence. And this part of the project is pretty trivial for us because of sklearn, and it allows us to focus on features and interpretation and the actual wildfire science. Okay, better go a little faster. So the next one, this field now, what I call ecological projection, is probably where I'm going to spend a lot of the rest of my career, I think. So what this is it's using the global climate models, which are these incredible coding machines that allow us to peer into the future under different greenhouse gas emission scenarios out to 2100. Some of them go out to 2300. And to run that long into the future and to produce daily output of lots of variables, they have to compromise for computational efficiency by being coarser. So the typical spatial scale for these is about 100 kilometers. And that's too coarse for understanding how most ecosystems will be impacted. So for example, coral reefs have a lot of variation on the sub-kilometer scale. So for this project, we took output from 35 of the global climate models. We regridded them to 100 kilometers, and then we statistically downscaled them to 1 kilometer using satellite data that was at that resolution. So basically imprint the spatial pattern from the observational data onto the coarse climate model data. And then we wanted to answer the science question, for every 1 kilometer reef containing pixel of the world, what was the year after which extreme heat above ocean heat above a bleaching threshold. So once the ocean water gets hotter than a certain threshold over what the coral's used to, the climatological conditions, it will bleach. It will expel its algae symbionts, which make food for it. But their enzymes basically change when the water gets too hot. So then if there's sunlight, they'll start producing basically toxins, that these oxidative radicals that the coral animal can't deal with. So it expels them, and that's why it bleaches, and it can starve if it doesn't regain its symbionts quickly enough. So we wanted to use those global climate models to get a high resolution sense of what year was the last year after which, every 10 years you would get one of those bleaching events at that location, or every 5 years you would get one of those bleaching events. So it takes about 10 years for coral assemblages to recover from a bleaching event like that. And this is like the most optimistic scenario and threshold metric, and this is the least optimistic scenario and threshold metric. So two different greenhouse gas emission scenarios and two different return timescales. Oh, by the way, we made this plot with CartoPy, so that's another package I like. And yeah, we found one of the top line things we found was that over 99% of reefs under the greenhouse gas emission scenario SSP 3.7.0, which is probably pretty close to what we're on now. Maybe it's it's probably pretty close. So the most dire scenario is SSP 5.8.5. And this is the next one down from that. But we project that under that scenario, over 99% of reefs will experience severe bleaching level ocean heat at least twice per 10 years by 2036, which is just, to me, heartbreaking and astounding. If we went into what I call climate emergency mode as a society and stayed on the lowest emission scenario, which is looking every day less likely, then I think there would still be massive coral damage globally. But under that scenario, I think we'd stabilize with maybe a few percentage of coral reefs, which would probably be degraded. But then as temperatures started coming down after 2100, they would probably recover. Okay, and the last project I want to talk about really quick is basically applying these same methods to humans. So humans are a little bit like coral reefs and any animal on the planet, in the sense that certain environmental conditions, if pushed too far, we just cannot survive. And so, of course, our bodies, when it gets super hot, our bodies cool themselves. We're constantly producing about 100 watts of power, even when we're at rest. When we're working hard, like doing yard work outside or exercising, it's much higher than that. But let's just say quiescently at rest, we have to get that 100 watts transferred from our body into the environment. Otherwise, our body is going to heat up, has no choice, just like the planet has no choice but to heat up when there's an energy imbalance. And that leads to heat exhaustion. It can lead to multiple organs that fail. It can lead to heat stroke and death. So if it's very humid and it gets too hot and your perspiration system breaks down, that's a very dangerous condition. So we're using the projections of humidity and temperature from the global climate models on a daily basis to calculate wet bulb temperature, which is basically the temperature a thermometer would read if you put like a little wet sock around it, so that the drier it is, the more that moisture would evaporate and cool the thermometer. So it's a very good proxy for sort of what our bodies care about. It's again important to do this at a much higher resolution spatially than 100 kilometers. So we just started this project really like basically a month ago, and we're using satellite data from an instrument called VEERS, from which we can infer 2-meter air temperature at the neighborhood scale. So we're going to try to do it at 375 meters. See, there's a really strong social climate justice aspect to this too, because most affected people, poor people, vulnerable people, almost by definition, live in the hottest neighborhoods with less trees, with more pavement, with a higher urban heat island factor. This is a previous work from Mora et al. 2017. And I wanted to point out that it's at 1.5 degree resolution, so roughly 150 kilometers. They did a really nice fit of heat waves, humid heat waves that at least one person died within, which they called deadly. This is the 90% confidence line, so it's very conservative. This heat map here is humid heat waves that didn't result in any deaths that were known. Then the team used this threshold to make projections under the different climate scenarios for how many days per year in the decade 2090 to 2100 would be beyond that deadly heat threshold. And so this is what they found for the 8.5 RCP 8.5 scenario, which is again sort of the most extreme scenario. But what I'd like to point out is, 100. This is what 100 kilometers of 2-meter air temperature look like. This is what 5 kilometers look like, and this is what 375 meters looks like. So we can just get so much more information by going to this high resolution. And again, so I'm using a Rio X-ray for this, and similar to the David Romps lifting condensation level code, we're using some code for calculating wet bulb temperature, which turns out not to be trivial, but was available in Python from experts who derived it, which is incredible because that would have taken a really long time to derive, and I would have had a lot of questions about whether it was really the right way to do it. So to have an offering like this from an expert, it's so wonderful. Okay, so really quickly, a couple of random thoughts before I end. With Pangeo, and I haven't delved very deeply into the Pangeo toolkit, but I get ease of use and functionality, and I also get scalability basically for free for large data sets. We know how to do open source. We're still figuring out how to do open science. So we have another grant to kind of create an open science framework out of the ecological projection methods that I talked about very, very briefly. So I also wanted to point out too that, the way I've done earth science data analysis has typically been the old school. You just download all the data you need onto a server locally and then do your analysis. As data volumes get bigger, and I probably should have had a plot of how quickly data volumes are growing, this will not be sustainable. And I think it's already not sustainable for a lot of scientists who don't have access to those levels of storage and that level of internet connection speed, especially in the global south. Personal gripe of mine, I don't know what's up with the Conda package manager. I don't know if it's just me for not being enough of a Python nerd or something, but man, it sure killed me when it stopped working, and I really don't like having to struggle with the environment being out of whack. So I asked some of my colleagues what packages they love, and I've used some of these. I haven't used others. So I use Pandas and GeoPandas. I've used Bin Statistic before. I've never used Seaborn or TensorFlow, but or Scikit-Image, but some of my colleagues love these other packages. And that probably shouldn't. I'm glad I'm virtual, and because you guys would throw your tomatoes and stuff at me for saying this, but I'm starting to get kind of interested in Julia. It's like Julia Curious. And the main thing we are wondering is if we can get significant performance enhancements, because for the data fusion, for example, as the data volume goes up, we're going to start running into some serious walls with performance. So that's at the top of our mind. And for the same reason, climate models are still mostly in Fortran because it's just ridiculously fast. And yeah, like I said in the beginning, I'm grateful that I could just be kind of a take advantage, I guess, of all of the great packages and code that you're writing. And I wanted to say too that I'm really happy to be talking to you, and it's fun to do this. But I don't want to let the fact that I'm seem happy to distract from the fact that, in my opinion, global heating is the greatest danger facing humanity. So with that, I'll end. Sorry I didn't end a little earlier, but maybe we have time for a couple of quick questions.
Thank you, Peter. That was wonderful. I do have a few questions for you from Slack. Let me move the microphone a little.
I'm going to stop my screen share just so you can see.
So you will look like our giant overlord. That's perfect. So there's a question from Scott Collis. So he said, "Hey Peter, great talk. Regarding open science, have you heard of the new NASA TOPS project? And if you're planning on engaging with them, it's a NASA-wide transition to open science."
Yeah, so I have, and I am starting to engage a little bit, but I haven't gotten as engaged as I would like to be. So I operate a little bit more at the science analysis, sort of just like writing proposals and then hopefully getting grants and then writing papers. And it's actually really interesting because it's sort of a haphazard way of doing science. And so there are, I'm starting to get involved with one possible sort of kind of science data system, which will be working kind of in a sort of service architecture in the clouds, trying to make some of the things that I have to do over and over again, like matching up different data sets, which is a pain to kind of provide that as a service, and to do it all with open science. So I should be shorter. My answer is yes, I do know about it. Not like a big player in it, but that will probably change over the coming years.
Cool, thank you. Question from Andreas Mueller. Did I get this correctly, that the takeaway from the coral part was that 99% of corals will die probably before the middle of the century?
Unfortunately, yes, that is basically our result. So what we're doing is we're inferring that the ocean heat waves will be beyond these severe bleaching thresholds. And so that inferring from that, yes, that suggests that they will die. There's also a possibility that some species will be able to handle the heat more than others. And so we might have sort of degraded communities in some areas.
Cool. Well, not cool, but thank you for your answer.
It's really weird, actually. I want to just follow up on that too. When I switched from astrophysics, it was strange to go to talks and hear about this really scary stuff, and to talk about the methodology and to not talk about how it affected us emotionally. But I think a lot of climate scientists are freaking out, but don't really know how to. I don't think we, as a professional group, we don't know how to talk about that to amongst ourselves. Like if I can talk about it here because I'm speaking on my own behalf, but when I was a really junior scientist, to stand up in the back of the room when somebody was talking about, ice sheets disappearing, for example, and to say like, what are we doing about this? It's just like, what can that person say? What can the other people in the room say? And so those conversations don't really happen, which is kind of makes sense, but it's also kind of weird. And I've always felt like I wanted to interact at that level, sort of as a professional group too, but we're still, it's so overwhelming that we don't even really know how to, I think, talk about it. We do it over beers, of course.
Okay. Let's go for one more question from Jonathan. How do you expect or hope that this research will impact policy? It seems that policy already lags so far behind the science.
Yeah, so it's interesting. My journey has really been from astrophysics to cloud physics, and then I guess getting more towards the core of stuff that freaks me out the most, right? Which ultimately the top of my list is just extreme humid heat, partly because I personally don't like heat waves. I don't think my body handles them that well. So I'm hoping that the high resolution projections of extreme humid heat, which so far hasn't been, I don't think the public understands it well enough. I don't think policymakers understand it well enough. It's kind of an appreciated clear and present danger, in my opinion. So I'm hoping that work, if any science can sort of wake people up to how dangerous of a situation we're actually in, I think it would be the extreme humid heat work. I mean, if that doesn't work, I kind of got nothing right after that. I mean, I think people studying food systems and crop yield losses in agriculture, they also have a claim for being some of the scariest, I think, projection science. So that's why, again, I personally feel that it's important for scientists to start engaging in other ways as well. And I've tried a lot of things, and the civil disobedience was really frightening to do, but it was, because of that, it was much more effective, I think. It's a form of communication between, so as a scientist, I see what's coming, and I write papers, and I'm like, why aren't people responding to this? And why aren't they responding to the IPCC reports? And when I did the civil disobedience, along with the hundreds of other scientists around the world, it was like kind of a Vulcan mind meld, right? Like, people understood, oh, okay, they really are worried. When you stand up and you show plots, even like the scary plots that I showed you guys, and you do it in the way I did it, which was to just talk about it sort of scientifically, I think the public has a hard time kind of making that connection between the plots and the emotions, right?
All right, thank you, Peter. Thanks for waking up really early to be with us this morning and for keynoting SciPy. It was a pleasure to have you. Good luck to all of us. So that's it for the keynote this morning. The tools plenary is starting now. Thank you.